Breaking news tonight as quantum AI scans have confirmed that interstellar object 3I/Atlas is not natural at all.
While the entire world is hypnotized by the glow of 3I Atlas streaking across the sky, a quiet alert slips through the noise, one that almost no one notices. An anonymous source claims NASA isn't watching the comet at all. They're digging into Yellowstone. But why Yellowstone? What did they detect beneath those boiling pools? And why did NASA mobilize teams in the middle of the night, before the world wakes up from its comet obsession? A far more unsettling question rises from the ground. What did NASA really find inside Yellowstone, the park that hides its secrets? Well, Yellowstone is often described in simple images: geysers erupting into blue sky, long lines of bison crossing the road, tourists standing behind wooden railings, photographing steam rising from the earth. But scientifically, Yellowstone is one of the most complex and least understood environments on the planet. Beneath its calm, postcard-friendly surface lies a constantly shifting system of boiling water, rising gases, mineral-rich vents, and microbial communities that operate under conditions lethal to almost every other form of life. This is what makes the park invaluable to researchers, especially those connected to NASA's astrobiology programs. The region sits on top of one of the largest volcanic systems on Earth. Water that seeps into the ground is superheated by magma, circulates through mineral layers, and re-emerges carrying chemical signatures from deep within the crust. Each pool, each vent, each hydrothermal basin has its own temperature, pH, gas concentration, and mineral composition, conditions that mirror environments scientists believe existed on early Earth and may still exist on Mars, Enceladus, or Europa. For astrobiologists, Yellowstone is not a tourist attraction, it is a living laboratory. In recent months, several specific basins have drawn more attention than usual. Research notes from visiting biogeochemists mention unusual stability in ultra-hot springs that normally fluctuate seasonally. Satellite thermal scans have shown minor but persistent heat anomalies in areas not typically associated with rapid change. The park's own scientific team has recorded small chemical deviations in water sample, variations not large enough to indicate danger, but significant enough to indicate a shift in underlying conditions. None of these findings were alarming on their own, but when viewed collectively, they suggested that something was evolving beneath the surface. This is where NASA's role becomes important. Their teams have historically used Yellowstone to test sampling equipment and study extremophiles, organisms that thrive in acidic, boiling, mineral-heavy waters. Some of these microbes contain pigments, enzymes, and metabolic pathways that are unlike anything found in moderate environments. When NASA arrives, it is usually for clear, predictable research cycle. But this year, equipment was moved in earlier than planned. Field specialists arrived from labs normally focused on planetary analog missions. Portable analytical instruments used to identify microbial structures and chemical compounds in the field were documented at two basins where they are rarely deployed. Yellowstone hides its complexity under steam and silence. To the public, nothing looked different, but to researchers who follow the park's seasonal rhythm, the patterns were shifting, and NASA's increased presence aligned precisely with those shifts. That combination created the first real indication that the anonymous message was referencing something grounded in measurable change, not speculation. In a place known for natural extremes, subtle deviations are often the signs that matter most. The leak that should have broken the internet. When the anonymous alert first appeared, it wasn't the dramatic language people associate with online conspiracy. There was no claim of extraterrestrials, no theatrical countdown, no attempt to sensationalize. The message was almost clinical. NASA escalated operations inside Yellowstone's hydrothermal zone after registering an anomaly during microbial sampling. That tone, measured, technical, and specific, is what separated it from the usual noise. The problem was that it surfaced at the exact moment the world was drowning in comet content. Anything not labeled 3I Atlas simply vanished from public conversation. But inside scientific circles, the message moved differently. Researchers familiar with Yellowstone's biology noticed that the wording aligned with real terminology: hydrothermal anomaly, sample deviation, accelerated microbial response. These terms appear in legitimate field reports when scientists encounter unexpected data in extreme environments. What caught their attention even more was the mention of accelerated operations. That phrase is rarely used casually. It implies that normal research timelines were shortened because of findings that demanded immediate follow-up. A few specialists began comparing the leak with publicly accessible research logs, environmental bulletins, and remote sensing data. This wasn't internet sleuthing for entertainment. It was genuine, scientific cross-checking, and the pieces aligned uncomfortably well. A research permit modification filed just weeks earlier had expanded sampling rights for a specific area near a high silica spring. Another document showed an unscheduled instrument swap, replacing standard probes with high-precision sensors typically used when fine-scale chemical changes were anticipated. These were details only relevant to people who understood hydrothermal biology, and they were precisely the kind of details mentioned in the leak. The leak also referenced unexpected isotopic shifts in collected samples. This single detail drew the most attention among professionals. Isotopic data is foundational in geology, microbiology, and planetary science. Shifts in isotopic ratios can indicate biological activity, chemical alteration, or interaction with previously unrecorded microbial processes. Yellowstone has produced unique isotopic signatures before, but they are extremely rare and always carefully documented. The suggestion that new shifts emerged and that NASA was leading the response was enough to raise the stakes. Where the general public saw another internet rumor, specialists saw a message written in the language of actual field research. It didn't provide conclusions. It didn't name a discovery. It simply pointed toward an event that required urgent scientific attention, urgent enough that NASA adjusted its schedule. And while the world remained fixated on the glow of an interstellar comet, this leak pointed to something happening under boiling groundwater on Earth, something that demanded silence, speed, and rapid coordination, something that, if verified, could reshape the way astrobiologists interpret conditions for life beyond our planet. In another moment, the leak would have gone viral, but overshadowed by 3I Atlas, it became the warning almost no one noticed. NASA's obsession with boiling pools of life. To understand why any anomaly inside Yellowstone would draw immediate NASA attention, you have to understand what the park represents in modern astrobiology. For decades, NASA's search for life beyond Earth has focused on one fundamental question: what kinds of organisms can survive in extreme environments, and what chemical signatures do they leave behind? Yellowstone is one of the most important places on Earth to study that question because its hydrothermal systems recreate the same physical and chemical conditions expected on early Mars, Europa's deep ocean vents, and volcanic exoplanets. The key is in the water. Many of Yellowstone's hot springs reach temperatures between 70 degrees Celsius and 90 degrees Celsius, sometimes more. These waters carry silica, sulfur, iron, arsenic, and other minerals at concentrations lethal to most known organisms. Yet within these boiling pools live highly specialized microbial communities, thermophiles, hyperthermophiles, and acidophiles, life forms adapted to heat, acidity, and mineral saturation at levels that challenge textbook biology. Some of these microbes form colorful mats, visible even from boardwalks. Their pigments protect them from intense heat and ultraviolet radiation. Others live deeper, invisible to the naked eye, thriving in chemical gradients that require specialized instruments to detect. Many of the enzymes discovered in Yellowstone microbes have become essential to biotechnology, including DNA amplification processes used in labs worldwide. NASA studies them not for medical reasons, but because their survival strategies resemble what scientists expect to find on hostile planets. The Atlas Obscura report that first made Yellowstone's new research publicly visible highlighted NASA's long-term interest in these extremophiles. Researchers collect samples to analyze unusual proteins, observe metabolic pathways, and determine how organisms adapt to brutal environments. One primary goal is to identify biosignatures, chemical patterns that might help future missions detect life on icy moons or ancient Martian lake beds. This is why the anonymous leak was taken seriously by experts. If NASA accelerated operations due to unexpected isotopic shifts or microbial behavior, it implies that something deviated from known patterns. Yellowstone extremophiles are diverse, but they follow identifiable chemical rule. A shift outside that range means either a new metabolic process was observed or an unknown organism was detected, both possibilities with major implications for the design of planetary life detection instruments. NASA's attention isn't random curiosity, it's strategic. Yellowstone is one of the few places on Earth where biology pushes its limits so far that it nearly crosses into what we classify as alien. Every new finding from these boiling pools influences how missions search for life in the solar system. So when NASA changes pace inside Yellowstone, scientists know it isn't a minor adjustment. It usually means data has appeared that challenges what they believe was possible in extreme environments. And that, combined with a silent comet distracting the world, is what makes the recent shift impossible to ignore. Movements after midnight. In scientific fieldwork, timing is usually predictable. Researchers operate during daylight, follow scheduled sampling windows, and coordinate with park officials to avoid disrupting visitor access. That is why the recent nighttime activity in Yellowstone drew attention from people who routinely monitor the park's research patterns. Movements documented well after closing hours are highly unusual for hydrothermal studies, especially when they involve specialized equipment rather than standard environmental sensors. Several independent observers, photographers, wildlife researchers, and even a few geothermal enthusiasts reported seeing portable analyzers, sealed storage units, and protective gear being transported into restricted areas near certain high-temperature springs. None of this behavior was inherently alarming, but its timing was out of rhythm with normal scientific practice. When NASA teams work in Yellowstone, they typically operate publicly and during standard hours because transparency is a key part of collaborative research. The deviation from that pattern aligned too closely with the timing referenced in the anonymous leak. One detail stood out. The equipment being moved wasn't designed for geology. It was designed for microbiology and chemical isolation. Portable mass spectrometers, sterile containment cases, and mineral deposition sampling kits were identified in photographs taken from a distance. These tools are used when researchers expect to collect delicate biological material that could degrade rapidly if not processed immediately. Bringing them in overnight implied that time-sensitive samples were either being retrieved or already undergoing analysis. Park staff later confirmed unusual access requests from external researchers, but the specifics were sealed in research agreements. That confidentiality is typical for unpublished scientific work, but not for simple equipment tests. Combined with the late-hour activity, it suggested that the research teams were operating on data that required immediate replication or validation, an approach only taken when preliminary results deviate sharply from expectations. The movement was not limited to equipment. Several basins were temporarily rerouted with no detailed explanation, and the signage used resembled hazard management protocol rather than standard area closed notices. Small environmental monitoring units appeared near vents that had shown stable readings for years. These weren't seismic devices or thermal sensors. These were instruments designed to detect changes in gas composition and microbial productivity. All of these details, once viewed collectively, pointed towards something specific, a response to biological or chemical findings that required tight control and rapid follow-through. Not secrecy for secrecy's sake, but caution driven by unexpected results. From a scientific standpoint, such activity doesn't automatically imply a breakthrough. But when nighttime deployments, specialized equipment, rapid sample retrieval, and expanded restricted zones all happen at the same time, and when the world is distracted by an interstellar comet, it becomes clear that something inside Yellowstone shifted the normal research dynamic, and whatever prompted those movements was important enough that NASA didn't wait for morning. The readings that didn't match anything on Earth. Scientific anomalies usually fall into two categories: instrument error or environmental fluctuation. Yellowstone researchers are familiar with both. Hydrothermal systems shift constantly: temperature, pH, mineral saturation, gas output, microbial density. Because of this, scientists build large margins of error into their measurements. When a reading falls outside that range, they repeat the test. When the test repeats the anomaly, they investigate further. What happened during the most recent sampling cycle is that several unrelated measurements reportedly diverged from their expected profiles at the same time. The first indicator involved isotopic ratios in dissolved gases. Yellowstone vents often release carbon dioxide with predictable carbon isotope signatures shaped by geological and microbial processes. According to the information that circulated among specialists, one sampling run showed ratios inconsistent with both volcanic degassing and known microbial metabolism. Outliers by themselves aren't uncommon, but persistent outliers, recorded across multiple instruments, are. That triggered the first internal alert. The second deviation came from mineral precipitation patterns in a high-temperature spring. In Yellowstone, minerals such as silica and sulfur typically deposit in stable rings as water cools. A few researchers familiar with the region noted that recent patterns deviated from their established geometry. Instead of forming smooth gradients, some precipitates displayed abrupt shifts in composition, suggesting rapid chemical reactions occurring at depths that normally show slow change. That implied the possibility of an active process, biological or chemical, altering the water before it reached the surface. The most significant detail referenced in the leak involved unusual microbial cluster behavior. Yellowstone extremophiles are well documented. Their growth curves, pigmentation responses, and heat tolerances are mapped extensively. But according to the summary shared privately among a small group of researchers, one sample showed a metabolic signal that didn't align with any previously catalogued thermophilic community. The deviation was subtle but distinct, chemical traces indicating energy extraction from compounds not typically used in known Yellowstone ecosystems. For NASA, this is the type of shift that demands immediate follow-up, because alternative metabolic pathways are exactly what planetary scientists look for when designing life detection instruments. None of these anomalies, on their own, would justify accelerated operations. Combined, they formed a pattern strong enough to require verification by teams trained in both microbiology and astrobiology, and the timing deepened the urgency. Yellowstone's hydrothermal chemistry changes seasonally, meaning unusual readings must be confirmed quickly before the environment resets and the data is lost. This is why NASA intensified field activity, not because of speculation, but because the readings didn't match known terrestrial behavior. The concern wasn't that the data hinted at something extraterrestrial. It was that the data hinted at something unfamiliar, even within one of Earth's most studied extreme ecosystems. In research, unfamiliar results are not ignored. They become the priority, the distraction of the century. When the anomalous data appeared inside Yellowstone, the scientific teams involved were working with urgency. Yet outside that environment, the world was consumed by something else entirely. The rise of 3I Atlas dominated headlines, live streams, and social media. The comet's growing brightness, unusual trajectory, and interstellar origin made it a global spectacle. Every outlet, from academic journals to entertainment channels, shifted their focus upward, and that public obsession unintentionally created a perfect information shield around whatever was happening beneath Yellowstone's surface. This isn't unusual in science. Major astronomical events often overshadow terrestrial research, especially if the Earth-based findings are technical and require careful analysis before going public. But in this case, the contrast was especially striking. While millions debated comet density estimates and tail composition, Yellowstone researchers were dealing with data that suggested a shift in one of Earth's most important analog environments for astrobiology. NASA's public statements during this period were standard: information about 3I Atlas imaging opportunities, mission updates, and routine commentary about comet observation. Nothing hinted at the intensified Yellowstone work. Meanwhile, park bulletins continued to issue neutral, low-detail updates about ongoing research activities. They contained no explicit references to isotopic anomalies, metabolic deviations, or chemical irregularities. To the casual reader, everything appeared normal. This imbalance in public attention had a significant consequence. It meant that early discussions about Yellowstone's anomalies occurred mostly within specialist communities: microbiologists, geochemists, astrobiologists, and field researchers. They analyzed satellite thermal maps, cross-referenced water chemistry records, and shared speculation in private channels. But nearly all of this conversation stayed out of mainstream view. Even when hints of the anonymous leak reached a broader audience, it struggled to compete with comet fever. Clips of 3I Atlas passing behind atmospheric haze routinely pulled millions of views. Posts about Yellowstone research barely reached beyond niche forums. The internet was primed for spectacle, not for slow, data-heavy scientific developments in boiling groundwater. This created a rare moment, a scientifically significant event unfolding in one of the most monitored natural environments on Earth, while the global spotlight was fixated on a celestial visitor millions of kilometers away. The distraction was not engineered, it was circumstantial, but it effectively softened public scrutiny around NASA's Yellowstone presence. For researchers used to working under intense expectation, the timing was both convenient and troubling. Convenient because it gave them space to operate without premature public pressure. Troubling because it raised an uncomfortable question: if findings in Yellowstone carry implications for how we search for life beyond Earth, shouldn't the world be paying attention? Instead, the sky stole the moment, and the ground kept its quiet secrets. The question that refuses to go away. By the time the Yellowstone research teams completed their initial verification cycles, the global conversation had only intensified around 3I Atlas. Telescopes streamed live feeds, scientists debated interstellar composition on morning talk shows, and millions waited for the comet to reach its closest visible point. In that atmosphere, almost no one noticed when a set of field instruments inside Yellowstone registered yet another irregular reading, similar in pattern to the earlier anomalies, but measured in a different basin entirely. The repetition ruled out coincidence. It also meant something deeper was influencing the hydrothermal chemistry. For the researchers involved, this created a scientific tension that rarely emerges in real time. The data did not indicate danger. Nothing pointed to geological instability or volcanic escalation. Instead, the signals pointed toward biological or chemical behavior not fully accounted for in existing models of extremophile ecosystems. That kind of finding is scientifically significant, but it is not something a team can announce prematurely. Every data point must be validated, replicated, and analyzed under controlled conditions. This is a slow, meticulous process, far slower than the pace of public speculation around a bright interstellar comet. Internally, the anomaly triggered a shift in research focus. Some teams began prioritizing deep-profile chemical scans. Others concentrated on isolating microbial signatures from water samples that behaved unpredictably during laboratory testing. A few researchers noted that the anomalous readings resembled patterns expected in theoretical models of early Earth biochemistry, scenarios often used to predict how life might emerge in environments beyond our planet. It didn't confirm anything extraordinary, but it emphasized why NASA was involved so directly. Yellowstone's hydrothermal systems are one of the closest natural analogues for environments where extraterrestrial life could exist. Outside those specialized circles, however, none of this entered mainstream awareness. The information remained fragmented, partially due to research confidentiality, partially due to timing, and partially because the world's attention had drifted toward a glowing object streaking across the night sky. The comet became the story. Yellowstone became a footnote, but even as 3I Atlas continued to dominate headlines, the lingering question from the anonymous alert refused to disappear among those who understood the science. What exactly triggered NASA's rapid response? Data irregularities alone do not create mobilization. Deviations do, patterns do, repeated anomalies do, and that's where the uncertainty remains. The findings inside Yellowstone may turn out to be the result of a newly discovered microbial process or a rare chemical pathway. They may be an early clue toward understanding how life adapts under extreme conditions, or they may represent something far more unexpected, something that reshapes how scientists design instruments for future missions to Mars, Europa, Enceladus, and beyond. The comet will pass, its spectacle will fade, but the questions rising from beneath Yellowstone's boiling ground will not. They remain unresolved, sitting at the intersection of geology, biology, and astrobiology, waiting for the moment when the world finally looks back down.